Okay, so I'm going to be doing a video on a elastic and an inelastic collision type of problem. So I'll be doing two videos, or two questions on this one video. So let's start with number one. We're going to treat this problem as a one-dimensional elastic collision. So again, from your notes, an elastic collision is one where we will assume that no energy is lost. And that the objects basically you can consider to be bouncing off of each other. An inelastic collision is a collision where energy is lost either through deformation or maybe the object breaks. For example, if you think of a piece of Play-Doh that just falls and hits the ground, it's going to smush a little on the bottom when it hits the ground. It's going to deform. That takes energy. So there's energy lost during the collision to the deformation of the Play-Doh ball. Another way you can think of inelastic collisions are collisions where the objects stick together. So there doesn't have to be deformation, but it could be an idea where the objects stick together after collision. So I'm going to do one of each. This one is a bullet. So here we will have a piece of wood, and a bullet is going to strike the piece of wood. Now it's going to actually emerge, and I'm trying to show that that vector is a little smaller. It's going to emerge at a lower velocity. So, and there's no friction on the ground. So we would assume, just think logically for a second here, that if this has some big velocity vector v, as the bullet moves through this piece of wood, it's going to impart some of that momentum to the wood, causing the wood to maybe move forward a little bit to have a velocity, and it's going to emerge with a lower v. All right, so that's just kind of just conceptually what's going to happen here. So this is a conservation of momentum question. So the way we do these is just think about this. We have the momentum before has to equal the momentum after. So the momentum initial equals momentum final. In this case, we're not losing any momentum to any other type of impulse being done. So this is just going to be the momentum of the system. Well, we have two objects on the system. So this is going to be the mass of the bullet times the velocity of the bullet, plus the mass of the wood plus the velocity of the wood. And this is that was initial. I mean, I suppose I could go like this to make them initial, but. And then now that has to be equal to the total momentum afterwards. So this is what it might look like, with my subscripts being B for bullet, W, and I for initial, W for wood. Okay. So the initial momentum of the system is going to be 0.023 times 230. Now, the wood block was at rest. It was stationary. So I'm just going to put 0 for the initial momentum of the wood. The bullet is going to emerge with less velocity than it originally had, and the wood block is 2 kilograms. Okay, there it is. So this is what it's going to look like. Now it is basically just a straight calculation question. So 0.023 times 230 equals minus 0.023 times 170 equals, divided by 2 equals 0.69. So V final equals 0.69 meters per second. Okay. So that's how we would do just a basic conservation of momentum with an elastic collision. Let's jump down and let's try to find a fun inelastic collision. Let's do something simpler, since this is an introductory video. Let's say, okay. Number 5. So here we will have object A colliding with object B, and they are going to stick together, and we're trying to figure out which direction they go and at what speed. So this is sort of a picture of how it will look. So again, the momentum initial has to equal the momentum at the end. And it looks like we're not doing any, we don't have an impulse on the system, so it's going to be MAVA plus MBVB has to equal the final stuff. Okay, so now here we're going to be a little bit careful, and I'm glad I stopped before I went too far, that they stick together. So this whole thing right here really functions as one object because they lock together. So we're going to be a little careful here that this will now be MA plus MB. Remember, they lock together, and since they lock together and travel together, they're only going to have one final velocity. So this idea right here is what separates elastic collision equations from inelastic collision equations. The elastic, we kept them as two separate objects, and they could obviously have two separate velocities. Here, they're going to function as one. Okay, so again, now this just becomes a straight calculation question. So 10,000 times 24 plus, it's an identical car, so 10,000 times a negative 16. We do got to be careful about our velocity vectors. And that has to equal 10,000 plus 10,000 V final. So this is really going to be 10,000 times 8. I'm just combining these two terms right here. I'm just redoing the math on this a little bit. And that's going to equal 20,000 VF. So 80,000 divided by 20,000, you're going to have 4 meters per second. Notice that the positive here is important, so this is a situation where they will continue to go this way. And if you think about it, that makes perfect sense. That this one right here was going faster this direction than this one was right here. This was going 24 and this was going negative 16. So it makes sense that the final velocity would be in this one's direction. It makes total sense with the conservation of momentum. And that is how we do our introductory elastic and inelastic collision problems.